Hi folks, welcome back to 6.1 Area Between Curves. Now hopefully you've already watched the first video on how to find the area for question number 6, but we're actually going to do this again with that different perspective, like what happens if we use dy instead. And so what we're going to do is I'm going to outline or shade the area that I'm interested in again. So I'm interested in this area right here. And for a clearer explanation of why this area and not the other ones, go back to the dx video for number 6. But last time we were here, we drew some vertical lines and we realized that we had to split this region up into 2 different areas in order to find the total area. But let's see what happens if we draw some horizontal lines or think about what we could do with dy. So if I draw this horizontal line, I notice that the right curve is blue and the left curve is red. Let me try a few more to make sure this pattern holds true. This horizontal line has a right curve of blue and a left curve of red. And so does this tiny one up here. Left curve of blue, right curve of red. So this one actually seems like a very good candidate to use that area equals the integral of c to d, so y values, of the right curve minus the left curve, dy. All right. Now, we're going to have to do a little bit more work for this one because we need to take both of these equations and we need to make them x equals, not y equals, okay? So let's pick the right curve first. So the right curve here is the blue one. And so let's take this equation, and if I write it like y equals 3/2 minus x over 2, let's start to solve for x. So I'm going to multiply both sides by 2. And I'm going to get 2y equals 3 minus x. I'm going to add the x. I'm going to subtract the 2y. And this is the function that I can put in for the right curve. All right, well, what about the left curve? So the left curve is in the red. Ooh, so many arrows. And I'm going to go ahead and do the same thing where I have y equals the square root of x. And I'm going to isolate x instead of isolating y. And I'm going to do that by squaring both sides. So y squared equals x. So y squared is what I can plug in for the left curve. Now what about my bounds? Well, the bottom of this shape has a y value of 0, and the top of this shape has a y value of 1. So c is going to be 0 and d is going to be 1. All right, so the integral from 0 to 1 of 3 minus 2y minus y squared dy. Now if you go back and look at example number 6, doing it with dx, I think we had to do the integrals were just a touch harder. But in this case, if we simplify, we'll get 3 minus 2y minus y squared dy, which means that we just have to use a lot of power rule here, and there's not even any fraction power, so that's really nice. So 3 becomes 3y. 2y becomes y squared, and y squared becomes 1/3 y cubed. And we're going to drop the bar, put a 1, put a 0. All right, these are even really nice numbers to plug in. 3 times 1 minus 1 squared minus 1/3 times 1 cubed. That's my f of d, minus 3 times 0 minus 0 squared minus 1/3 times 0 cubed. And that is my f of c. Now, this happens pretty frequently, but when I plug in 0, a lot of the terms, if not all of them, tend to go away. And so that gives me 3 minus 1 minus 1/3, or 2 minus 1/3, or 5/3, which was the same answer that we got using the other method. So let me zoom back out so you can see this alternate method. Now I would say that this is part of what I want you to study, and that is how to make the decision about which one's going to make your life easier, okay? Personally, for number 6, I probably would have done dy. However, I know it's something you kind of have to develop and think about, but if you can find one that is consistently on the right and on the left, that's a good indicator that you want to use dy. On the flip side, if you find a curve that is always on the top and then another one that's always on the bottom, that's a really good argument for dx, okay? So that's it for the 6.1 practice. Let me know if you have any questions, and I'll talk to you soon.